All right, so good morning, students. This video is going to go over the notes from yesterday, which I felt were still more confusing than I wanted them to be. So what was tough about this, we're reviewing the entire chapter, reviewing all of chapter 5. Now, if you look in your book, you'll notice the order they went in is not necessarily the same order that we went through. Personally, because I thought it was kind of weird to introduce E as the very first day when it's just this weird number. It's a little bit strange. But we've done all this stuff. We did logarithms. We're going to review all this stuff. So base E, logarithms, how to transform the graphs, basically moving them, the properties of logarithms. So our review yesterday, we sort of went through all of this, and this video is going to sort of clarify that. The second video we'll make today is going to go over specific homework questions. So let's jump into it. The book said, what is E? It's going to start talking about E first of all. And what the hell is E? Well, what E is, before we can talk about it, I think you sort of have to talk about this equation. Now, this is an equation that's probably one of the ones I use the most because money is something that comes up in our daily lives. This is for long-term investing. If you're investing like 10 years at a basic interest rate, this equation is what you'll get. We use this equation in Math 1. We used it in Math 2. We saw it again this year. But we're going to make this more advanced. So your starting amount, 1 plus your rate, which was 12%, and then over T years. And then at that point, you plug it in, and the calculator does the rest of the work. Not much to explain there. So you should be familiar with that equation. What it is, though, this equation, let me flip over. This equation is if it's compounded one time per year. What that means essentially is, let's say you put in your money on January 1st, you wouldn't get the interest until maybe later on in the year. Let's say December 31st, okay? So say you had to wait the whole year to get your 12% interest. Now, 12% is not much. It's 12 cents on the dollar. But if you have millions of dollars, 12% is now $120,000. That's a big difference, okay? So someone said, well, instead of giving me my rate at the end of the year, what if I wanted to do it 4 times a year? What we call quarterly, okay? Or you could do it every month, so 12 times a year. Or you could do it every day, 365 times a year. It's just this rate divided over another period of time, and it affects our equation that way. Okay, if you're going to do it 4 times a year, same equation, just put a 4 and a 4 here. You'll get a little more interest. Not much, like I said, unless you're a millionaire, then it'll be a noticeable amount. So what someone did says, hey, let's focus on this. 1 plus is something over n to the n power. And if you focus just on this part of that equation, sort of factor out just this part of this, factor out the r and the t, if you just focus on this, what happens is, as you plug in 10 here, you get 2 point something. Plug in 100, you get 2 point something something. Plug in 1,000, what you eventually get is, it doesn't grow and grow and grow and grow. Eventually it levels off, and you get this number, 2.71828. Okay, so what does that mean? Again, if you calculated your interest more often, you would get this part of the formula. And when this part of the formula is isolated, and you plug in larger and larger numbers of n, you can try this out. Plug in 10, plug in 20, plug in 30, and you'll see what it gives you. So to show you what I mean here, I'm using Desmos as my calculator here, the scientific calculator one. All right, here it is. 1 plus 1 over 10 to the 10th power gives you 2.59. As you crank this up, you might think, oh, well, it's going to get bigger and bigger and bigger. And you put it to 100, it gets 2.7. Okay, so it did get a little bigger. Let's make this 1,000, 1,000, 2.71. Let's add another 0 and another 0. So you get 2.718. This is already getting pretty close to what E is. The idea is that calculus will go over this more, but the idea is the higher numbers you get, this thing does not get bigger than 2.7. We've sort of reached our limit. You can keep on adding zeros if you want. You can put in 1 million under here, 10 million, 100 million. Doesn't matter. It's going to level off. Okay, it doesn't matter what you put in there. It's going to level off. And so that's where E comes from. Okay, whoops, wrong place. Okay, here we go. That's where E comes from. Okay, so when we're looking at this, you'll evaluate this a little bit more. All you really, really need to know to get through this is that E is equal to this. It comes up in your calculator, and it has to do with money equations, but it has to do with a lot more. There's more videos on E that I loaded to the classroom because people can explain it more than me, because they know more math than me. Where it comes up also for us is with ln. ln is nothing more than a log with base E. You don't write that, though. At some point, they call it natural log because it comes up so often in nature. Again, the other videos will explain more of why. I'm just going to show you the how of the math. Okay, so that's what E is. E is just a number, and that's where it comes from. The Chapter 5 review, then, it gives you this equation right about this. Y equals E to the 0.5x. Now, again, just remember, E is just a number. Anytime it bothers you, just remember, okay, it's just 2.718, and if you want more, 28 something, something, something. All right, 2.718 is going to be good enough for us. So it's just a number. The book has uses exponential growth or decay. We're used to both of these equations for growth and decay. One's plus for growth, one's minus for decay. And the whole thing is, this part inside here, if it's 1 plus something, it's something more than 1. If it's 1 less, then it's less than 1. So if we're doing this equation, you got E. E is more than 1, so that's got to be growth. It's got to be growth. I'll say that again. It's essentially the same equation here. You're like, where's the A? Well, let's put a 1 for the A. Well, what's the 1 plus R? Well, that's E. So now it looks just like this form, sort of. A little. 1 plus R, in this equation, they're using E. Either way, it would be a growth equation. Now, they give you this, and you say, okay, what about negative E? Sorry, E to the negative X. Well, a negative exponent just means flip-flop it. Again, 3 to the negative 2 would be 1 over 3 to 2. This is the rule. This is the definition. It's what it is. That's how they define negative exponents. So if you have this, you can rewrite it as this. And you're like, I still don't recognize this. Well, this could be written as this. And again, what you have inside here, it doesn't look like 1 plus R to the X. In fact, I messed up. Because this is less than 1, it must be 1 minus R. 1 over E would be something less than 1. So we must be dealing with this equation. So it must be decay. Now, is there an easier way? Yes. If you're more visual, graph them. E to the X will be growth. E to the negative X will be decay. So if you have access to a calculator, double check it. If you're not sure. Okay. But it will look like this. Decay will be going down, growth will be going up. The next thing you saw in our notes yesterday was logarithm graphs and exponential graphs. So log graphs looks like this, but you don't recognize that. We've done enough exponentials in Math 1 and Math 2, hopefully, and Math 3 for a semester. Did you recognize exponential looks like a skateboard ramp? It's flat on this side and it shoots straight up towards vertical on this side. Not exactly vertical, but it looks like it's almost vertical. So 2 to the X we know. Now let's say you forgot that. Make a table of values. I put more than we need probably, like 0, 1, 2, 3, but I want to put some negatives. Put in 0 for X, you get 1. Put in 1 for X, you get 2. Put in 2 for X, you get 4. And so on. Why did I do that? Well, what I know is, I know these two graphs are inverse of each other. These are inverse of each other. So once I know the 2 to the X, I know logs are inverses, so I flipped it. I flipped the whole thing. Okay. We didn't go too much into inverses, but logs are inverses of exponentials. Logs are inverses of them. So the table of values would be easier to switch, and then the graph would be flip-flopped. It ends up looking like this. One of the easy points you can check is 0, 1 becomes 1, 0. Okay, the x, y here got flip-flopped over here. The x, y's here got flip-flopped over here. Instead of negative 2 and 1/4, it's 1/4 and negative 2. Okay, so that's how you can get the graph of logs. But in general, all log graphs are going to look something like this. All log graphs are going to have this type of shape. just like all exponentials look something like this. Okay, we didn't put it here, but 3 to the x, 4 to the x, 5 to the x, they all look the same. They're just a little bit steeper. Okay, but they all go through that point. Same thing here, they would go, you'd have slightly different graphs. Okay. But they would be generally the same shape. That's what you need to know about log graphs. Okay. Next thing we did with them was, okay, let's focus on this. Let's recall. If you had 2 to the x and you knew what that was, then adding 3 at the end, that's a vertical shift. And we're going to review that again. But whatever your graph is, plus 3, it will just shift the whole thing upwards, up by 3. So instead of 1, it went up by 3. Not up to 3, it went up by 3. So instead of 1, it became 4. All right. So let's practice that. Let's cover this up. What we did is we looked at these, okay, this is what we're going to call your parent function. Or your mother function, if you prefer. Parent function is what the book says. We like to say mother function because it's more fun to say. So the mother function is a log graph. So you already know the shape is that. Okay, that's what you know. A log graph will be shaped like that. Subtracting 5 inside or adding 3 at the end, we know what these do. Inside things always give a left or right shift. Outer things always do an up or down. So this is always horizontal and this is always vertical. You're like, wait, where'd that come from? That came from the previous chapter. We spent a lot of time graphing in the first semester so we could get used to that. So what this means in terms of the graphs is, if this was your original in red, your parent function, adding 3 would shift everything up. So instead of this point being at 0, it would go up 3 units. Whereas this one, minus 5, actually shifts it by 5 units. So instead of crossing at 1, it crosses at 6 because that shifted 5 units. If that's confusing, just think of Algebra Cat here. In general, he says he likes to think of parabolas. He hates logarithms. That's just who he is. Anyways, the parabola function, we've done this before. Go back in your notes and you see if you have it. You should have it from Math 2 and from this year. But we did a lot with parabolas, and the rules work the same. What are those rules? In general, they look like this. In general, just as before, the number in front was a vertical shrink or a stretch. Number inside was always horizontal. And number at the outside was always a vertical shift. And again, if you're the cat and you're thinking about parabolas, it's pretty much the same, except for instead of, it doesn't have the word log here, it has an exponent. Same thing. Same thing here. We have e as our base, but essentially the same thing. Take a look at the variables I used. H is being subtracted from x, and it's left-right shift. Same thing here. H is being subtracted from x. And same thing over here. K is just the number added on at the end. K is a number added on again. A is always the number right in front. So it's not easy now, obviously. But once you get used to these, it's a little easier. So it won't matter if you're talking about exponential or logs. Doesn't matter. A number inside is a horizontal shift. A number outside is a vertical shift. That's the rule. Okay, so finally let's get back into what the hell are logarithms anyways. Logarithms are confusing as heck for everyone. Okay? If you get them right away, that is excellent. You are in the rare crowd who gets it already. We start with something we know. 2 to the third equals 8. We can change that into log form, and most students would say, why would you do that? I like it this way. Why would you do it this way? The reason is because, this is really the answer for why we do this. If you have 2 to the x equals 11, 11's prime. It's not a multiple of 2, so I don't know what the answer is. If we change it to this form, our calculator is built to do these things. Our calculator is built to do these things. You'll see I have a button here. Log with the 2 blanks. You can totally do that. You can see on my calculator, this calculates me, type it in exactly as it is, and there's my answer. I don't know how it got that, because it's a calculator.